You're listening to With Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists, and they're going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. If you're reading about correct PCB layout techniques in most technical literature, there's a very good chance that you're going to read about multi-stage filters and blocking capacitors for supply pins of digital ICs. However, real measurements or practical simulations are often missing. So the goal of this application note and podcast is to show the influence of the design, the number of ground vias, and also the placement of the MLCC filter components to each other. Furthermore, it'll be shown that an unfortunate dimensioning of capacitor banks can cause more problems than initially expected. And blocking capacitors at supply pins have that task to close the clocked current loop of the digital circuits locally in the shortest way with the help of a low impedance. This reduces the radiated magnetic field strength and the RF interference currents coupled into the supply voltage level as much as possible. If the capacitors are optimally selected with regard to their impedance curve and also geometrically optimally placed at the VCC pins, then the clocked RF current can be blocked in the best possible way. To demonstrate the various influences in practice, the insertion loss S21 was determined over a wide frequency range from 300 kHz to 3 GHz using a 4-layer PCB designed for exactly 50 ohms impedance. In addition, 2 supporting simulations were created using the freeware LT Spice as well as the professional tool EMC OS. This was used to determine how close one can get to the real measurements using E5071C, which is an ENA RF network analyzer, and what influence the via positioning has relative to each other. The MMCX connector types from Worth Electronic were selected as RF connectors. First, we'll discuss the circuit diagram and the measurement setup. Our first demonstration board has 6 measuring channels. The schematic of the demo board is shown on YouTube and our Worth Electronic podcast page. The top 2 channels are for calibration of the measurement setup. The third channel is for measuring the oscillation which occurs when several MLCCs are connected in parallel. In addition, it's also to be compared to what extent Class 1 NPO/COG differs from that of Class 2, the X5R or X7R ceramics with otherwise identical component values. In the remaining 5 channels, we always use the same 0603 high-frequency surface mount ferrite and 2 100 nanofarad X7R MLCCs. However, differences can be found in the number of GND vias, the design, and in the geometrical arrangement of the MLCCs. Basically, the higher and more broadband the insertion loss S21 is, the better the effect of the entire filter and or the individual blocking capacitor. Since the same ferrite and the 2 100 nanofarad MLCCs are placed everywhere in all 6 measurement channels, then the insertion loss in the measurements depends on 1, the design of the MLCCs, especially their ESL, 2, the number of vias to GND, and that means more vias equals lower parasitic inductance to GND, 3, the arrangement of the MLCCs to the ferrite, and 4, the length of the traces to the MLCC pads, and that adds up to the ESL of the MLCC. The smallest MLCC designs, 0403, with 3 vias per GND pad, are expected to give the best result because their equivalent series inductance, or ESL, is the smallest. The largest MLCC designs, 0805, with only 1 via per GND pad, are expected to have significantly worse insertion loss above the resonant frequency. The worst result is expected from the measurement channel with the 0805 MLCCs in combination with the poor layout. Here, the only single GND via was used for both MLCC's GND pads. In addition, the MLCCs are arranged in parallel with the ferrite, resulting in parasitic inductive and capacitive couplings. Furthermore, the trace connections of the MLCC pads are unnecessarily long. 1 to 2 millimeter in length corresponds to approximately 0.5 nanohenry of additional ESL. This illustration shows the parasitic impedances caused by the design and the layout. For the measurement channels with the capacitors of the 0603 types, results are expected which lie between the 0402 and the 0805 types. In addition, a measurement channel was designed to investigate the effects of several MLCC capacitors of Class 1 ceramic with different capacitances connected in parallel. In this comparison, one 100 picofarad, one 1 nanofarad, and one 4.7 nanofarad were selected. Since these are particularly high Q capacitors where the dielectric is titanium oxide, unfavorable resonances between the various capacitive and inductive elements of the capacitors are expected. These resonances would greatly reduce the insertion loss S21 in certain frequency ranges. Furthermore, the same experiment was performed with MLCCs with Class 2 ceramics. X7R ceramic is made of barium titanate. Since the ceramic is more lossy than Class 1 ceramics and thus has a slightly lower Q, a less pronounced resonance amplitude is expected. Worth Electronic has been providing a wide range of suitable LT SPICE models for most of the passive components for many years. These can be easily downloaded from the Worth Electronic website at any time. If the vias and their parasitic properties are added to the models in LT SPICE, the waveforms of the real S21 measurement can be reproduced pretty accurately. However, this only affects the relative and not the absolute insertion loss. The parasitic inductance and parallel capacitance of the vias depend on their length and inner diameter. In addition, the vias also influence each other by a mutual inductance, which mainly depends on the distance between the vias. The further the vias with the same electrical potential are away from each other, the smaller is their mutual inductance and thus also the total inductance. A supporting simulation was also performed using the EMC OS software, and this is available for a fee. Among other things, this software must be fed with the exact PCB raw data from the CAD, such as Altium. With the help of the EMC OS software, the effect of different positioning of the 3 GND vias was investigated. In theory, vias with the same electrical potential are expected to form a mutual inductance, and thus the total inductance increases the closer they are placed to each other. If the vias are placed at a 90-degree angle around the GND pad of the MLCCs, they can be connected close to the pad and still result in a large distance between the 3 vias. As expected, the smallest layout 0402 in combination with the several vias per GND pad provides the best result due to the smallest ESL. The insertion loss of the bad layout example turns out to be blatantly worse than the rest. Depending on the measurement point, there is a difference of more than 40 decibels to the next best channel. If the basic layout rules, such as 90-degree arrangement of MLCCs to ferrite and short pad connection to vias, as well as traces are observed, then a broadband filter can be successfully designed. The differences in the insertion loss are then only maximum 10 decibels depending on the design as well as the via count. The relatively simple LT SPICE simulation can nicely represent the basic properties of the different measurement channels, but it's still not 100% accurate. The many parasitic properties of the connectors, the PCB, so on and so forth, these cannot be easily represented in LT SPICE. The comparison measurement of the 3 MLCCs in NPO and X7R also shows the difference in quality in a particular way. Although the NPOs achieve better values in the insertion loss at the individual resonant frequencies, the amplitude deflections are also higher in negative form. The NPO MLCCs generate an LC resonant circuit with higher Q, which in certain frequency regions brings with it the danger of an unwanted amplification of interference components. From the differences shown, it can be seen that this pi filter can only work optimally if the textbook layout rules are followed. There are differences of over 40 decibels depending on the frequency in the insertion loss, which in practice can mean the difference between success and failure in the EMC measurement. What has not been considered in this application note and podcast is the voltage dependence of the Class 2 MLCCs, as well as the DC current dependence of the chip bead ferrite. These influencing factors mean further differences in insertion loss in practice. Now, if you want to successfully block supply pins on digital ICs, it's recommended to use several vias per GND pad on the capacitors. In addition, it's also been shown that very short stubs to the capacitors and a geometrically unfavorable arrangement also significantly worsen the blocking quality. The ferrite and the capacitors should be arranged at 90 degrees to each other to avoid unwanted coupling. With the help of the EMC-OS simulation, it was shown that GND vias should be placed as far away from each other as possible, but also close to the MLCC pad. This way, a few decibel attenuation can be achieved in the higher frequency range. The best result was achieved by placing the vias 90 degrees around the GND pad and with a small distance at max of 0.3 millimeters to the pad. The broadband insertion loss without undesired oscillations also shows the enormous advantages of chip bead ferrites over pure capacitor groups. If a designer still wants to connect several capacitors in a group, this group should contain a Class 2 capacitor in order to limit the resulting oscillations in amplitude. However, a sufficiently high insertion loss can only be achieved with an additional chip bead ferrite. You can find capacitors, ferrites, and LT Spice models available at Worth Electronic online. And for any questions, click the icon to talk to our live chat team. To view the materials and replay this podcast, visit www.we-online.com/podcast. You're listening to Worth Electronics What's Up Radio Podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up Podcast.